Good morning. This is Nuclear Plant Components. And today we're going to begin our discussion on heat exchangers. So heat exchangers are devices that are used to transfer heat from one fluid to another fluid. So two requirements or two facts about the nature of heat exchangers. I'll abbreviate HX from now on for heat exchangers. One, heat can only be transferred from one substance to another when there is a temperature difference between them. Secondly, heat is always transferred from the higher temperature substance to the lower temperature substance. So in heat exchangers, heat is transferred primarily by conduction or convection. Conduction is the process of heat transfer between interacting adjacent molecules of the material through which the heat is being transferred. So it's like a physical touching. Convection is the transfer of heat by a process of bulk motion and mixing of macroscopic portions of a fluid. For example, if you heat air and hot air rises, then the hot air that's rising begins to mix with the cooler air that's higher, and then the process repeats, and that's an example of convection. So heat transfer from a hotter temperature fluid to a cooler temperature fluid That's the direction which heat flows. So there's two general types of heat exchangers. So you have surface heat exchangers versus direct contact. So for surface heat exchangers, the two fluids are separated by a solid surface. Say a tube or metal plate. So there is no direct contact between the two fluids. Then you have direct contact heat exchangers. The two fluids come into contact with each other. Let's start with shell and tube heat exchangers. These are a surface heat exchanger. So they work by they transfer heat from one fluid through a surface to another fluid at a lower temperature. So example of some shell and tube heat exchangers in a power plant would be, let's see, examples would be feed water heaters or condensers. So in the shell and tube heat exchanger, the shell forms a casing around the region where heat transfer occurs. So the fluid that flows inside of the tubes is called tube side fluid. And the fluid flowing On the outside of the tubes is the shell side fluid. So in shell and tube heat exchanger, a large number of tubes are used to increase the surface area. This is a key term, and we'll come back to that a little bit later. But the key term here is surface area for heat transfer. So when several tubes are used in a heat exchanger, they make up a tube bundle. And there's several arrangements of the tubes. You have straight tube. Here, the tubes are arranged in a bundle and enclosed by the shell. Straight tubes allow easy mechanical cleaning of the tube interiors and can be easily removed for replacement. Another type of tube arrangement is U-tube bundles. And these tube design, the tubes are free to move back and forth within the shell when heated and cooled. Some disadvantages are they are difficult to mechanically clean the surface, and it's difficult to replace a U-tube. Some other more examples of tube arrangements, you have coil tubes, flowed tubes. So the largest, typically speaking, the largest Schilling tube heat exchanger in the plant is the main condenser. It has thousands of tubes that carry the circulating water. So the way the fluids flow through the heat exchangers, there's different types of ways. So we have single pass heat exchangers. This is when the fluids pass each other only once. And you have multi-pass. And this is when fluids pass each other more than once. And a pass occurs each time either fluid flows across or along the heat exchanger's length. So you can have single pass tube and single pass shell. These are some examples. You can have a two pass tube and single pass shell. And you can have two pass tube and two pass shell. So for example, in a heat exchanger, so in a single pass tube, single pass shell, this is shell side. This is tube side. One pass along the length. Or a two-pass tube and a two-pass shell. This is the shell side. It made two passes along the length. And the tube side, once again, two passes along the length. Yes, two passes along the length. So we'll talk now about flow classifications. So we have parallel flow. This is when the two fluids in a heat exchanger are traveling in the same direction. You have counterflow. These are when the two fluids travel in opposite directions. And then you have cross flow. This is when the two fluids are traveling at right angles to each other. So for parallel flow heat exchanger, the fluid on the shell side and the fluid on the tube side both flow in the same direction. So if we have a heat exchanger, through the tube, if you have your fluid of the tube side, this is the tube side temperature coming in, T1, and T2 is your tube side temperature going out. And that's the direction of flow. For your shell side, temperature coming in, capital T1. This is the direction of flow. And then your shell side temperature leaving, T2. So incoming temperatures are 1, leaving temperature is 2. Incoming state is 1, leaving state is 2. So then the temperature profile of parallel flow heat exchanger looks like this. Let's go to another page. So our temperature profile, y-axis is temperature, x-axis is tube length. So as the fluids flow along the tube length, and remember we have lowercase t1 and t2 is the tube side fluid entering and leaving. Uppercase T1 and T2 is the shell side fluid entering and leaving. So for the tube side fluid, we'll say this is the cooler fluid, and the shell side is the hotter fluid. So remember, heat flows from the hotter fluid to the cooler fluid. That's the direction of heat flow. And for that to happen, there has to be a temperature difference between the two fluids. So as the hotter fluid leaves, we expect the temperature to be cooler. As the cooler fluid leaves the heat exchanger, we expect the temperature to be warmer. So the temperature profile for the cooler fluid looks like this. The temperature profile for the entering hotter fluid looks like this. So this would be my hot fluid entering, T1, and leaving, and my cooler fluid entering and leaving. And it's for parallel flow. So when the cold fluid, or cooler fluid we'll call it, enters the heat exchanger, the rate of heat transfer is large due to the temperature difference. delta T, what we refer to temperature difference, which is just your final temperature minus your initial temperature, or a temperature of one stream minus a different stream, is a difference in temperature, delta T. Delta means difference. So as heat is transferred from the hot fluid to the cold fluid, the temperatures become closer together and their delta T becomes smaller. So in this case, we're talking about the delta T difference in temperature between the two streams or the two fluids. So in parallel flow, the rate of heat transfer decreases as the fluids travel through the heat exchanger. One more thing to note, in parallel flow, the cooler fluid temperature is always less than the hotter fluid temperature. And we can see that on our graph. The purple line represents the temperature profile of the cooler fluid flowing through the tubes will never be greater than the temperature of the shell side fluid in a parallel flow heat exchanger. So counterflow heat exchangers. So once again, my tube side flow direction. So you have your cooler fluid entering the tubes, lowercase t1 entering cooler fluid temperature, lowercase t2 exiting. Let's say tube side cooler fluid. And then this is counterflow. So in this case, the flow is not running parallel. So my entering T1 of the temperature of the warmer fluid, flow direction is in opposite of direction of the cooler fluid. And my exiting fluid temperature for the warmer shell side fluid. So it's counterflow. And how this temperature profile looks. X-axis, once again, is tube length. Y-axis is temperature. So as my cooler fluid flows down the tubes, it gets warmer. So my lowercase t2 is greater than the entering tube temperature, which makes sense. So this would be my T2, T1 of the cooler fluid. And counterflow, the shell side temperature enters at a higher temperature than it leaves, which makes sense. So that's one thing we can readily see as opposed to parallel flow heat exchangers. The cooler fluid enters the heat exchanger where the hotter fluid leaves or exits the heat exchanger. Therefore, the hot fluid exit temperature can be below the cold fluid exit temperature. And remember, this is impossible. This statement is impossible with parallel flow heat exchangers. So, rate of heat transfer equation, U sub O, A times delta T. Q dot is whenever you see a dot on top, you know that typically talking about a flow rate or a rate. So rate of heat transfer typical units, say BTUs per hour. U sub O is the overall heat transfer coefficient. A is the surface area of heat transfer. Remember, we're talking about surface heat exchangers, not direct contact. And remember, we said earlier we were going to come back to the surface area and discuss that a little bit further. And delta T, in this case, is the difference between, always specify what you mean by delta T. In this case, delta T is the difference between the shell side average temperature and the tube side average temperature. So if you want a higher heat transfer rate, and this is all multiplication here, increasing any of these terms will increase your heat transfer rate. And we talked earlier about surface area, A. If you increase that, you can increase the heat transfer rate. So in cross flow heat exchangers, Once again, your tube. Direction of flow. Your cooler. Tube side. Fluid. Then you have your entering hotter shell side fluid. Remember, cross flow, they flow at right angles, and you're exiting shell side hotter fluid. Remember we said cross flow, one fluid flows perpendicular to the second fluid. And how this temperature profile looks. Once again, x-axis is tube length. Y-axis is temperature. You're entering and leaving tube side temperature. Entering and leaving shell side temperature. And the question may ask, well, why isn't the shell side temperature changing? Typically, these cross flow heat exchangers are used where a fluid changes phase. So say, for example, condensing a fluid or evaporating a fluid. So remember we spoke in an earlier lecture about latent heat versus sensible heat. And you can add heat to a substance, say water, and it will increase in temperature. Let's go back quick. Adding heat to, say, heat to liquid water will increase the temperature until you get to the boiling point, right? Or saturation point. Here you start to have a mix of vapor and liquid water. Any heat added at this point does not increase the temperature of the water until the phase change is complete at constant pressure. So basically, liquid water at a constant pressure, as you increase the temperature, as you increase the heat added to it, the temperature increases. But once you get to the saturation or boiling point, any additional heat added will not cause an increase of the temperature of the liquid water. It just assist in changing the phase, liquid water to vapor. And the opposite is true as well, which would be condensing the water vapor back to liquid water. The heat removed, you have to remove heat. And that's what the heat exchangers do. Either add heat, cross flow, either adding heat to get a condensing phase change or evaporating phase change. So going from liquid to vapor or vapor to liquid. So regenerative versus non-regenerative heat exchangers. So regenerative is one in which the same fluid is used as the cooling fluid and the fluid that is being cooled. And non-regenerative the hot fluid or hotter fluid is cooled by a colder fluid which is supplied by another system heat exchanger startup. So this is operation of a heat exchanger. So before a heat exchanger can be operated, it must be filled with the operating fluids when doing so, you want to minimize the thermal expansion between the tubes and shells. Therefore, want to gradually introduce the fluids. Thermal shock occurs when the temperature of the fluid in a system subtly increases or decreases causing an expansion or contraction of the metal. Heat exchanger vent valves must also be open while filling a heat exchanger. This lets air escape. Fluid hammer or water hammer occurs when the velocity of a fluid flowing in a system suddenly changes. This is minimized, or water hammer is minimized by slowly opening and closing valves and keeping fluid systems filled and vented. Heat exchanger shutdown. To shut down a heat exchanger, the flow of the hot fluid should be gradually reduced to zero. Then the flow of the cold fluid should be stopped. So let's talk about some typical components in a nuclear power plant. So you have steam generators. So steam generators, I'm going to abbreviate SG. Generators are typically vertical shell and tube heat exchangers. Heat is transferred from a single phase fluid at high temperature high pressure on the tube side to generate a two-phase mixture at a slightly lower temperature and pressure on the shell side. With the primary focus to transfer heat from the reactor coolant system and produce steam to drive the main condenser. Main turbine. And we're obviously talking about a pressurized water reactor. So there's two basic types of steam generator design. You have U-tube steam generators and once through steam generators. So some benefits of the once through steam generators produce superheated steam. So no steam drum is required. Production of the superheated steam improves steam quality, which lessens corrosion in the turbines. Some benefits of the U-tube design. The volume of water maintained in a U-tube steam generator at 100% power is much larger than NN when it's through steam generator. Condensers. So main condensers, once again, are large vacuum tight shell and tube heat exchangers. And in condensers, low pressure steam is exhausted over the tubes while circulating water flows through the tubes. The shell side of the main condenser is the steam side, while the tube side is the water side. So it's two functions the first function is to provide a high vacuum environment for turbine exhaust steam, and two, to condense turbine exhaust steam so that it can be reused in the power cycle. In the main condenser, the cooling water can come from ocean, river, reservoir, etc. Condensing operation. So the condenser removes both latent heat and sensible heat from the turbine exhaust steam. And once again, remember, latent heat is associated with phase change, liquid to vapor, vapor to liquid, and sensible heat is associated with temperature change. So heat exchanger maintenance ensures that the necessary cooling and heating can be accomplished with that. So post-maintenance testing ensures that the heat exchangers are ready for operation. Some post-maintenance testing can include leakage tests, air testing, which checks for leakage, flow verification, see if the heat exchanger is capable of delivering the required flow. You got hydrostatic testing, to ensure all connections are capable of withstanding the normal operating conditions. Your vibration testing. Okay, we'll end here for today. If there are any questions, please do not hesitate to send me an email. Be safe.